So today we will take up a problem on the variable wall temperature case, and we will look at how to get the expression for the wall heat flux variation as well as the heat transfer coefficient. So let us take the example of a linear surface temperature variation, that is of the form T wall of x is equal to a plus bx. Okay. So if you plot the surface temperature as a function of x, so at x is equal to 0, that will be equal to constant a, and from there it varies linearly. Okay, so this is the value T wall at x is equal to 0, which is equal to a. So if you go back to what we derived yesterday with the Duhamel superposition integral, if you have a continuous variation of the wall temperature, so we have derived the expression for the wall heat flux. This was 0.331 into k by x, PR 1 by 3 and you have T wall at zeta equal to 0 minus T infinity plus 0 to x 1 minus zeta by x the whole power 3 by 4 minus 1 by 3 dt wall by d zeta into d zeta. Okay. So this is our expression, Now if for the limiting case where you do not have any slope, the slope is 0, so this is T wall minus T infinity, so this becomes equal to your flat plate with a uniform temperature expression. Okay. So of course if you have continuous variation but also intermediate temperature jumps, okay, so there you have to introduce an additional delta T into h, for those temperature jumps in between. Okay. So apart from that, this is the expression. Now we will substitute for the given temperature profile whatever we require. So for example, in order to evaluate this Duhamel's integral, we need to first get the slope of the wall temperature profile, and since this is a linear profile, it's very simple. So in this case dt wall by d zeta will be, for this particular profile, b, right. So we'll substitute this into equation, let us call this as equation 1. So this is T wall at zeta equal to 0 is nothing but a. Okay, so right at x is equal to 0, this is nothing but a. So I am just substituting for T wall at zeta equal to 0 as a minus T infinity plus integral 0 to x 1 minus zeta by x to the power 3 by 4 the whole power minus 1 by 3. Dt wall by d zeta is nothing but b, so this will be b into d zeta. Okay, so now all we need to do is evaluate this integral, because everything else is known. T infinity is given for this problem, whatever value it is known, a is a constant, b is a constant, so we need to find this particular integral, and this particular integral, whatever slope that you get and put it here, is of the following form, which we will reduce it to. So we can assume a variable z which is equal to zeta by x to the power 3 by 4. Okay. So I am just going to transform the variables again. So I am saying that zeta by x to the power 3 by 4 is equal to some other variable z. So therefore dz by d zeta should be equal to 3 by 4 zeta by x to the power 3 by 4 minus 1, which is minus 1 by 4 into, with respect to d zeta, if I, so x is a constant, so it will be 1 by x, right. So this is my derivative, okay. So therefore now I can substitute for d zeta in this integral in terms of dz, okay. So this will give me my dz is equal to 3 by 4 into x power, this is x power 1 by 4 minus 1, so this will be x power minus 3 by 4, okay, into zeta to the power minus 1 by 4 into d zeta. Alright, it is just I am just doing some algebraic manipulation there. So therefore now I can substitute for d zeta, I can transform these variables from d zeta to dz, okay. So I can substitute for zeta by x to the power 3 by 4 as z, and d zeta I can substitute in terms of dz. In fact I can also write this in terms of z, okay. Now z is zeta by x to the power 3 by 4, so z to the power of 1 by 3 I can put it, because this is already, yeah, so my dz will be d zeta 4 by 3 here, x to the power 3 by 4 zeta to the power 1 by 4, okay. So zeta by x, so I can write this as 1 by 4 x power minus 3 by 4, I can take 1 by 4 x, yeah, so I can write this as zeta by x the whole power 1 by 4, this is 1 minus, yeah, right, yeah, right, I can write it like that, because this is anyway 3 power 3 by 4, I can write it as x divided by x power 1 by 4, okay. So now this is nothing but zeta by x to the power 1 by 4 is nothing but z to the power 1 by 3, okay. So this I can rewrite as z to the power, this entire thing as z to the power 1/3, okay. So what I am doing is I am transforming all my variables from zeta plane to z plane, okay. So wherever I have z, that also I have to include that. So therefore if I substitute into this expression 0.331 a by x pr to the power 1 by 3 rex to the power, so you have a minus t infinity plus, so I am substituting for d zeta, so 4 by 3 is constant, 4 by 3 also b is a constant I can take out, and also inside the integral this is integrated with respect to now dz, therefore x also can be taken out of the integral. Now 0 to, this is originally 0 to x here, so I can transform this to 0 to 1, okay, because at so zeta equal to x, this becomes z equal to 1, so therefore this will be the upper integral will be 1, upper limit of integration, so this will be 1 minus zeta, 1 minus z, sorry, 1 minus z minus 1 by 3, and you have this z power 1 by 3 here, so that will also come outside 1 by 3 into dz, okay. Just check 1 minus z to the power minus 1 by 3 into z to the power 1 by 3 dz, okay. So now I have anyway transformed that to this integral right here. Now how should I integrate? So I will just give you the formula. Now this is of the form of what is called as a beta function. Okay, the beta function can be expressed. So generally the problems with the Duhamel integral will be of the form of a beta function once you transform the variables from zeta to dz. Okay, so you will be ending up with a function something like this, and you can express this beta function in terms of constants p and q 0 to 1 z to the power p minus 1 1 minus z q minus 1 dz. Okay, this is valid for positive values of p and q less than infinity. Okay, so this is how your beta function is defined. Okay, now if you compare this with this expression, you can see 1 minus z to the power q. So therefore q minus 1 is equal to minus 1 by 3, and p minus 1 is equal to 1 by 3, right? Therefore q is equal to 1 minus 1 by 3 2 by 3, and p equal to 1 plus 1 by 3 4 by 3. Okay, so therefore this p and q will be nothing but 4 by 3 comma 2 by 3. Okay, so therefore this entire term can be written in terms of beta function. Okay, we can write it again. Okay, so everything here as it is. A minus t infinity plus 4 by 3 bx into beta function. Okay, this entire integral is beta function. The parameters are 4 by 3 comma 2 by 3. Okay, so the integral is replaced by the beta. And why do we now need to write this in terms of beta function? Because the beta functions are tabulated. Okay, in fact very specifically the beta function itself can be expressed as a function of another function called the gamma function. Okay, so and gamma function tables are quite common. They are tabulated for different values of the function. So therefore we will express the beta function in terms of gamma function as follows. This is your gamma function. This is your beta function, where generally your gamma function gamma of say some variable s is represented as e power minus x x to the power s minus 1 dx. So this is your gamma function basically. Okay, and this has been tabulated. You can do this integral numerically also for different values of s, but these have been tabulated. Gamma function charts are there, so you can look up for the values that we have here. So therefore beta of 4 by 3 comma 2 by 3 will be gamma of 4 by 3 into gamma of 2 by 3 by gamma of what? 6 by 3, that is 2. Okay, so if you plug in from the gamma function tables which are available online, you can Google gamma function charts and you will find those nice charts for different values of this, for p and q. So if you plug in, you will get this beta of 4 by 3 comma 2 by 3 as 1.2087. Okay, So this is the resulting expression for beta 4 by 3 comma 2 by 3. So if you substitute that value into this, so this is 1.2087 into 4 by 3, which comes out as 1.612. Okay. So now we have a complete expression which gives you the variation of heat flux with respect to x, okay, provided you know your constant A and B and you know the free stream temperature T infinity. Alright. So now therefore from this the heat transfer coefficient can be defined, okay. So H of x can be defined as Q wall double prime x by T wall of x minus T infinity, okay. Now T wall of x minus T infinity can be written as A plus Bx minus T infinity. So therefore you have this entire 0.331 A by x Pr to the power 1/3 612 Bx, the entire thing divided by T wall minus T infinity, which is nothing but A plus Bx minus T infinity, okay. So therefore for the given constants you can now determine the local variation in the heat transfer coefficient, and for the limiting case where your B equal to 0, B equal to 0 gives me a uniform wall temperature, okay. So for that case how does it reduce? This becomes A minus T infinity here, the denominator this cancels with A minus T infinity here, B is anyway 0, okay. So then you will, what will be the expression? So constant wall temperature, that is 0.331 K by x Pr power 1 by 3 Rex power half, okay. So this is your constant wall temperature boundary condition. So for the limiting case where B equal to 0 you retrieve your constant wall temperature heat transfer coefficient, okay. So it's a very straightforward method as such, you know. So so what it finally means that, so you can also solve this by dividing this into piecewise constants like we did yesterday. You know, you can assume that you can represent this by piecewise constants like this. Right, you can divide this into piecewise constants, and instead of the integration that we did here we will replace this by discrete summation, okay. So if you do that you can also get somewhat similar expression, but that will be in a slightly discrete form. So in that case you will have something like .331 into K by x Rex power half Pr power 1/3 So this will be T wall 0 minus T infinity. So when you differentiate it, the original profile you have a phi, so that will be minus k d phi by dy at y equal to 0, which will be nothing but the heat transfer coefficient h. Okay, so that h you have already substituted as 0.331 k by x rex power half pr power 1 by third into 1 minus zeta by x the whole power minus 3 by 2 3 by 4. What is that? Can you go back and revise the expression for h of x? 0.331 k by x rex power half pr power 1 third 1 minus zeta by x to the power what? 3 by 4 the whole power minus 1 by 3. Okay, so this we had to substitute into the expression for q wall of x, which was so you had the original expression for T wall minus T infinity, that is your T minus T infinity was T wall 0 minus T infinity into phi of 0 comma x comma y plus summation of n equal to 1 to capital N delta T wall n phi of x comma y. So this was what we saw yesterday. This was for the local variation in temperature. We have superposed the solutions where you have a uniform temperature, okay, and one by one. So then the incremental temperatures. So all of that when we superpose, so first you have, this is the basic solution that you have plus the incremental solutions, which is basically this. Okay, so now when we want to calculate the heat flux, so we had to say minus k into d phi by dy at y equal to 0, which was nothing but the heat transfer coefficient h. So this we had to substitute into this expression. So therefore this is taken out as common. You have T wall naught minus T infinity as one of the terms, and the second term will be, the rest of the terms will be n equal to 1 to capital N number of discrete intervals. You have delta T wall n, okay, into 1 minus zeta by x the whole power 3 by 4 whole power minus 1 by 3. Okay, so this is what you will have if you have a discrete variation. If you had a continuous variation, you will replace this by an integral, okay, integral over d zeta. Okay, now you have a discrete variation, therefore you just substitute for delta t as it is, and of course the heat transfer coefficient for the first location where zeta equal to 0 there is no unheated starting line, so therefore you do not have this term for that. For the subsequent boundaries conditions you maintain at zeta equal to zeta 1, zeta equal to zeta 2, so there you have unheated starting line, so there you have to substitute the values of, so this will be corresponding value of zeta n. Okay, so by doing this also you can calculate your local wall flux variation. Instead of using the Duhamels integral method, you can just linearly superpose. This is the superposition method, right? So you can divide this continuous curve into small discrete intervals where you have variation of temperature like this. You can substitute that into this discretely, and you can also estimate the wall heat flux. Okay, so both will be more or less the same. The continuous is the more accurate because you are taking into account the slope accurately. Okay, so this is to just give an example, okay, how you take a problem where suppose you have a wall temperature variation like this, and you can use either the Duhamels integral or a simple superposition technique, and you can calculate your local heat transfer coefficient and your wall heat flux. Okay, so any questions on this? Okay, now for more complex profiles, it's more likely that most of the wall temperature variation cannot be approximated just by a straight line. It will be more complicated profile. So for a more complicated wall temperature variation, what is common practice is that we can approximate the wall temperature variation as something like power law series. So instead of using an A plus Bx relationship, we can write this as A plus summation n equal to 1 to capital N B n x power n. Okay, so this is a power series expansion. So which can be used to approximate more complicated nature of profiles. If you have a profile something like this, so you can use power series expansion. You can fit the coefficients to you can do a regression and fit the coefficients such that you can approximate this curve with the power series expansion. Okay, so this is a better way to represent this than using a straight line, right? So you can substitute this now into this expression here. So you had a term here dt wall by d zeta. So now you have to calculate dt wall by d zeta for this. So what will be the expression for dt wall by d zeta? Summation n equal to 1 to n. You have n bn x power n minus 1 or zeta power n minus 1. Okay. So this has to be now substituted into the expression where we had dt wall by d zeta. Okay, and if you do that, the resulting expression for the heat flux comes out to be, everything is the same, only you have the summation term 331 k by x so everything up to here is the same, except you have the summation term and everything inside the summation term goes there. So n equal to 1 to n, you have n bn. So now so this will be x power n minus 1 into, there will be an x which will come out of the transformation. Okay, so that will be giving you x power n. Okay, into the beta function will be there as it is. So you will have beta. Now this beta function also will become a function of n. Okay, so where this beta function can be written as gamma function of 4 by 3, originally it was 4 by 3, now it becomes 4 by 3 n into gamma function of 2 by 3 divided by gamma function of 4 by 3 n plus 2 by 3. Okay, so now depending on the value of n that you use, okay, so the value of beta will change and then you have to sum them over all the values of n. So suppose you are using 5 terms, you have to sum them for each value of n, and for all the 5 terms you have to sum them together. So and that will give you the variation if you have a more complicated profile. You can approximate that with the power series expansion, and you can use this expression to calculate the local heat flux variation. Okay, now the question is, given local variation in the temperature profile, we can use this to calculate the local heat flux, but what about the other way? Suppose your wall boundary condition is a locally varying wall heat flux. Okay, so how do you calculate the local wall temperature as well as the heat transfer coefficient? Okay, so that is also a little bit more complicated derivation. I am not going to do that. I will just only give you the final solution for the wall temperature variation. okay, for a non-uniform wall flux. So for this case you can calculate the wall temperature variation. You can express it as follows: 0.623 by K PR power minus 1 by 3 REX power minus half. You have 0 to x 1 minus zeta by x to the power 3 by 4 the whole raised to the power minus 2/3 into Q okay. So this is the local variation in the wall flux whatever you have, so that can be substituted into this and you can get the corresponding wall temperature variation. Okay, so this is this given in your textbook Case and Crawford. Okay, he has also not derived it, but I think there is a reference to some literature where they have done it and they have shown this kind of an expression. Anyway, so this is beyond the scope of your this thing, but you should understand that you can do either of these when using the approximate solutions given non-uniform wall temperature. How do you calculate the variation in the wall heat flux, or given a non-uniform wall heat flux, how can you calculate the variation in the wall temperature? So both are possible by using the approximate methods. So I think with that we will kind of wrap up the external laminar external flows, external boundary layer flows. So we have covered quite a bit. We have almost covered whatever possible similarity solutions under external boundary layers, and also the approximate methods. Whatever external laminar similarity solutions, they have a complementary integral methods also, integral solutions also. Like we have seen, if you have the Falkner-Skan solutions for wedge problem, you have similar Karman-Pohlhausen solution when you use the integral methods. Okay, of course, like the Blasius solution, there you can approximate some velocity profile and very easily find out the expression for say local Nusselt number. Okay, so whatever is possible, in fact you can also use the approximate solution for example a flow with transpiration. You have boundary where you have porous boundary with suction or blowing. So we have derived the similarity solution for that. In fact we have identified the condition for the variation of the suction profile, velocity profile, so that you can get a similarity solution. Okay, so the same way we can derive an approximate by using approximate method. We can derive expressions for the local skin friction coefficient as well as the Nusselt number variation with transpiration. So every similarity solution has a counterpart in the approximate methods, and more than that you can also derive some special cases such as the unheated starting length, which you cannot derive by similarity solutions, and also cases such as these where you have non-uniform wall temperature variation of any given profile, which you can approximate as a power series expansion or a non-uniform wall heat flux. Okay, so for these kind of boundary conditions, the similarity solutions are not possible or becomes very rigorous, so their approximate solutions are much easier. Okay, so this is in a nutshell giving you an idea what we covered. So from the next week onwards we will look at laminar internal boundary layer flows. Okay, so there actually strictly speaking the boundary layer concept doesn't have a meaning that the way that laminar external flows has. Okay, the strict definition of boundary layer flow doesn't hold for internal flows. Okay, because once you have a fully developed flow, both the boundary layers merge and everywhere you have viscous effects. There is no place where you can use potential flow and approximate that with the potential theory, and somewhere you can solve with the solving the full Navier-Stokes. Okay, so therefore we have to resort to a complete solution of the Navier-Stokes equations in some cases. In some cases we can make approximation to the velocity gradients or the temperature gradients. Okay, so there we can obtain exact solutions of reduced form of the Navier-Stokes equations. Okay, so that is also very important and interesting because most of your practical problems in heat transfer, okay, although there are many external flow problems, you will find most of the heat exchangers they are you will be encountering internal flows there, and in those cases you should understand the approximations that you can make and how you can get the expressions for local variation in the Nusselt number, and in say fully developed case how the Nusselt number variation, there is no variation in the Nusselt number and so on. Okay, so that we will cover in the next 9 to 10 classes starting from next week. So in about 3 weeks I think we should be able to cover the laminar internal flows, and then from the following week onwards, that is about the 4th week of March, Professor Kolar will start turbulent flows. So that will be for about 7 lectures or so, and or 7 or 8 lectures, and maybe natural convection for another 7 or 8 lectures.